Okay. So, today I shall continue with the same problem regarding computation of the shift in the modes or shift in the frequencies of oscillation within cavity resonator when the medium gets perturbed by small inhomogeneities and anisotropicities in the electric and magnetic fields, in the permittivity and permeability fields. So, here you have an anisotropic and inhomogeneous tensor. Anisotropic, inhomogeneous, permittivity and permeability tensor. That means your epsilon now becomes a 3 cross 3 matrix, which is a function of omega x, which is a function of omega x and y. I am not considering a z variation. So, this is represented by say epsilon alpha beta omega x y, this matrix 1 less than alpha beta less than or equal to 3. That means along the 3 different directions you have different refractive indices and they may vary from point to point within the resonator cavity. So, you have this sort of a situation where you have this is the z axis, this is z equals d, this is z equals 0 and this is the xy plane. And likewise for mu, you have mu is a function of omega xy, which is mu alpha beta, a function of omega xy 1 less than alpha beta less than or equal to 3. This is a 3 cross 3 matrix. So, you have an anisotropic and inhomogeneous permittivity and permeability tensor. So, what are Maxwell's equations? First equation is curl of E is equal to minus j omega mu, then here you have H. Okay, here mu is a matrix, H is a column vector with 3 components, and likewise you have curl of H is equal to j omega epsilon times E. So, epsilon is again a 3 cross 3 matrix which multiplies onto a 3 cross 1 vector. So, we assume that epsilon and mu are small perturbations of the homogeneous and isotropic situation. So, it is epsilon 0 is the 3 cross 3 identity matrix plus delta times a 3 cross 3 permittivity matrix, which is a function of omega x and y, and likewise mu is mu 0 into I3 plus delta times chi m omega xy. This is a 3 cross 3 matrix, is also a 3 cross 3 matrix, and delta is a small perturbation parameter. And you write down these Maxwell's equations and you take into account that E is proportional to e power minus gamma z and H is also proportional to e power minus gamma z. So, wherever dou by dou z comes, there you replace it by multiplication with minus gamma and you proceed. So, for example, if you write down the first Maxwell equation, you get Ez dou Ez by dou y minus dou Ey by dou z, that will become gamma Ez gamma Ey is equal to minus j omega mu Hx and the third component, say minus j omega mu and the first component x of this, which can be written as minus j omega mu xx or mu xx into hx plus mu xy into hy plus mu xz into hz. Likewise, if you write down the second the y component of the first Maxwell curl equation, namely Faraday's law of induction. So, dou Ex by dou z, the dou Ex by dou z will be replaced by minus of multiplication by gamma, dou Ex by dou z minus dou Ez by dou x minus dou Ez by dou x is equal to minus j omega mu yx into hx plus mu yy into hy plus mu yz into hz. Likewise, the third component, and for the second Maxwell curl equation in the same way. So, you get a set of algebraic equations. You get a set of algebraic equations for hx hy, ex ey hx hy in terms of Ez and its partial Ez hz and their partial derivatives. So, you can write the system as if you solve, you get a set of algebraic equations, we get a set of linear algebraic equations for Ex, Ey, Hx, Hy in terms of Ez, Hz, dou Ez by dou x, dou Ez by dou y, dou Hz by dou x and dou Hz by dou y, and when you solve them, you express your answer for Ex, Ey. Let us call it as E perpendicular. By E perpendicular I mean Ex into x cap, the planar components of the electric field, Ey, y, and likewise H perpendicular. You get them as minus gamma. It will correspond to the homogeneous case with some small perturbations coming from the anisotropicity of epsilon and mu. So it will be minus gamma by h square. What will be h square? H square will become a matrix in this case, right? If you write down, for example, curl of E can be written as del perpendicular plus z cap dou by dou z cross E perpendicular plus Ez into z cap. You can write it in coordinate free form also, and this is minus j omega. Then you can write it as mu it is minus j omega mu into h, right, and mu into h can be represented as if you write down the perpendicular part of this will give you del perpendicular Ez cross z cap, the xy components of this equation, plus z cap cross dou by dou z is minus gamma. So minus gamma del perpendicular Ez cross z cap del perpendicular Ez cross z cap minus gamma z cap cross E perpendicular is equal to minus j omega. Then if you write down the xy components, what do you get here? Mu can be represented as mu perpendicular, that is the xy, it is a 2 cross 2 matrix, mu xx, mu xy, mu by x, mu by y, that constitutes mu perpendicular. And then here you have mu xz, mu yz, and here you have mu zx, mu zy and mu zz. So it can be partitioned in this form, right. So if you where your mu perpendicular, by mu perpendicular I mean mu xx, mu xy, mu yx, mu yy. So this can be written as mu perpendicular, it is a 2 cross 2 matrix multiplied by h perpendicular. H perpendicular is hx, hy in column form, and then you will have a plus mu xz, mu yz multiplied by hz, right. So it is clear from this that your h perpendicular and E perpendicular are satisfying linear equations in terms of hz and Ez, and likewise by duality you get a similar equation for curl of h perpendicular, curl of h, and you get an equation like E is where by using the duality transformation, namely E goes to h and h goes to minus E. So when we solve these equations, we get E perpendicular as minus gamma by h square. So if you can solve it up to order delta square, so minus gamma by h naught square del perpendicular Ez minus j omega mu naught by h naught square del perpendicular to hz, that will be the unperturbed part, plus you will have a delta. If you expand up to order delta, you will get delta times, since the anisotropic part is of order delta, anisotropic and inhomogeneous parts of the permittivity are of order delta, you will get plus delta times something delta times some matrix let us call this is a 2 cross 2, this is a 2 cross 1 vector, right. So, it will be some matrix A1 which depends on omega x and y, which will depend on omega, it will also depend on gamma, of course, it will depend on omega, it will depend on gamma, it will depend on h naught square. So, this times Ez, it will be turned Ez into Hz, right. This is a 2 cross 2 matrix plus A2, there will be a linear term in Hz, Ez, Hz appearing without derivatives. So, omega gamma h naught square, then you have dou say A2, let us call it as A2 into dou by dou x of Ez Hz, plus A3, another 2 cross 2 matrix omega x omega gamma h naught square, and also it will depend on x and y, it will also depend on x and y because the perturbations in the permittivity and permeability, they also depend on x and y. So, this times dou by dou y of Ez Hz plus order delta square, which I am neglecting right now. I am assuming that the perturbations are very small, so that you retain terms only up to order delta. Likewise, you will get a term, you will get an expression for h perpendicular. Here your h naught square is nothing but omega square mu naught epsilon naught plus gamma square, and of course, you have to, in the end you have to assume that the electric field, the tangential components of the electric field vanish on the top surface, on the side surface, on the bottom surface, on all surfaces the tangential component vanishes. So, you get the condition that E perpendicular equal to 0 when z is 0 and d, you have Hz equal to 0 when z is 0 and d, and you have h normal, that means you will get an equation of the form h perpendicular. So, you will require that Ez vanishes, Hz vanishes, and you will also require that dou Hz by dou Ez by dou x, dou Hz by dou n. That means if you look at the, if you write down the same equation for h perpendicular and take the dot product with n, where n is the unit normal along the boundary, on the outward boundary. So, if you put the condition that Hn is equal to 0 at that point and use the duality to express h perpendicular in terms of the derivatives, partial derivatives of Ez Hz in the same way with respect to x and y and Ez Hz. So, you will get an equation of the form dou Hz by dou n, dou Ez, it will be of course cross z cap. So, you will get, so here the corresponding equation for h perpendicular will be of the form minus gamma by h naught square del perpendicular Hz plus j omega epsilon 0 by h square del perpendicular Ez cross z cap plus similar terms, instead of A1, A2, A3 you will get B1, B2, B3 plus delta times similar terms corresponding to the perturbations coming from the inhomogeneity and anisotropicity in the tensors, in the permittivity and permeability tensors. So, if you calculate h perpendicular dot n, you will get a dou Hz by dou n coming from n cap dot del perpendicular is equal to dou by dou n, the derivative along the unit normal. So, that should vanish on the surface because n cap cross, if you look at this term, n cap dot del perpendicular Ez cross z cap, it is same as del perpendicular Ez dot z cap cross n cap, and z cap cross n cap is t cap, the tangential direction. So, this will give you dou Ez by dou t cap is 0, which will follow from the equation on the boundary, which will follow from, that is you get dou Ez by dou t cap, that is anyway 0 on the boundary, because Ez vanishes along the boundary. If you take Ez at two neighboring points, the difference will also vanish, which means that the tangential derivative of Ez along the boundary vanishes. So, this won't first of give any problem, but for this to vanish you will require that del hz by del n cap becomes 0. You will also require that n cap dot this should vanish, and that will be guaranteed by the fact that hz vanishes, sorry, Ez vanishes on the boundary, and of course an auxiliary condition that okay, and that is okay, that is how the whole situation will look like. So if you write down the equations finally for Ez and Hz, if you substitute it in the third Maxwell equation, what is the third Maxwell equation? Del perpendicular plus z cap dou by dou z cross E perpendicular plus Ez z cap is equal to minus j omega. If you look at the third component, it is nothing but mu u zx mu zy into hx hy. So it will be nothing but h perpendicular. You are multiplying, you have a matrix, right, mu xx, mu xy, mu xz, mu yx, mu yy, mu yz, mu zx, mu zy, mu zz, and you are multiplying this by hx and then hy, which is h perpendicular, hx hy form h perpendicular and then hz. So that if you look at the last part, it is mu zx mu zy multiplied by h perpendicular plus mu zz into hz plus mu zz into hz. Okay. So if you substitute this into this equation, and likewise for h perpendicular and likewise for h from the curl equation for Maxwell's curl equation for h, or equivalently obtained by dual by applying the duality transformation to this equation. So if you look at the z component, this is the z component, on this side also you have to extract the z component. So this will become simply, it will become simply del perpendicular cross E perpendicular equals this. So if you substitute those expressions for E perpendicular and H perpendicular into this, you will get del perpendicular square plus H naught square. Okay, you will get del perpendicular square plus H naught square multiplied by Ez hz plus you will get a, okay, let me write down the whole thing. You will get del perpendicular square plus H naught square acting on Ez hz plus delta times a matrix, a 2 cross 2 matrix. Let us call this as F1. So F1x, which depends on omega, it will depend on gamma, it will depend on H naught square. So it will, if it depends on omega and of course if it depends on H naught square, it is equivalent to saying that it depends on omega and gamma. That is because H naught square has been written as omega square epsilon naught mu naught plus gamma square, and gamma in the end will be put as j pi p by d, because you require that the electric field, the Hz should vanish, when z is 0 and d, and you also require that E perpendicular, that means you require that dou Ez by dou z, that should vanish when z is 0 and d. You see, why should dou Ez by dou z vanish? When you write down E perpendicular, you get a term like minus gamma by H naught square del perpendicular Ez minus etc., right. So this minus gamma, multiplication by minus gamma is equivalent to taking a derivative with respect to z. So this can also be written as del perpendicular H naught square. You can write this as del perpendicular into dou hz by dou z. So that means that the partial derivatives of dou Ez by dou z with respect to x and y vanish when z is 0 and d, because E perpendicular should vanish on the top and bottom surfaces, Ex and Ey should vanish. So dou Ez by dou z should vanish when z is 0 and d. So your Ez will have a dependence as on z, as Ez will have a dependence on z as cos p pi z by d, whereas Hz will have a dependence as sin pi p z by d. So that the derivative of Ez with respect to z will vanish when z is 0 and d, and Hz will vanish when z is 0 and d. So you will get this sort of a thing, and you can express gamma in terms of h naught square and omega square. So it is equivalent to saying that this depends on omega and h naught square. This depends on omega and h naught square, and then this is of course h naught. This is called k, this is also denoted by k square. It is a constant. So this xy multiplied by dou by dou x, it's a 2 cross 2 matrix, f1y, it's a 2 cross 2 matrix. Let us call this as fx instead of f1x, it is not needed. Okay, it is fx fy. Okay, this is fy omega h naught square xy into dou by dou y. So this whole thing acts on Ez and Hz plus delta times you will have g, delta times g as a function of omega h naught square x and y, and this acts on Ez Hz to give 0 up to order delta square, where g is a 2 cross 2 matrix. In the isotropic case, in the isotropic but inhomogeneous case, this last term will not come, because you will not get into the Maxwell equations simply Ez and Hz without their derivatives, except in the third component of the Maxwell curl equations. So this is the sort of perturbation theory which we have to attack, and the boundary condition. So I can write this in this following way: I define a vector psi as a function of x and y to be equal to Ez as a function of x and y, and Hz as a function of x and y. I have extracted out for a fixed value of p, for a fixed value of the integer p which defines the mode along the z direction. So I am fixing the integer p which equivalent to saying that gamma is plus or minus j p pi by d. That means the dependence on z is of the form sin p pi z by d for the magnetic field and cos p pi z by d for the electric field. So if you write down the equations, the eigenvalue equations here in terms of psi, it will become h naught square into psi plus delta times fx into dou by dou x plus fy into dou by dou y into psi plus delta times g 2 cross 2 matrix into psi equal to 0. And what are the boundary conditions? Boundary conditions are that Ez should vanish on the boundary and dou hz by dou n should vanish on the boundary. So the Ez and Hz satisfy mixed boundary conditions. So you can see that with these boundary conditions your del perpendicular square becomes a Hermitian operator. It is very easy to see that. Why? So it is a self-adjoint and Hermitian or a self-adjoint operator. That is useful because you know that the eigenvalues of a self-adjoint operator are always real, and minus del perpendicular square is positive definite, which means that del perpendicular square is negative definite, so that its eigenvalues are all negative real numbers. So how do you show that it is Hermitian? Simply take two functions psi 1 and psi 2 and apply Green's theorem in the form psi transpose del perpendicular. Let us look at it this way, let us take it as star. So psi 1 star, star means conjugate transpose del perpendicular square psi 2 minus psi 2 transpose del perpendicular square into psi 1 star, and then you integrate this over the cross section of the guide, let us call that cross section as d in the xy plane. So d defines this whole region, this whole planar region. So this is equal to, by Green's theorem, integral along the boundary of d, which is S, along the boundary of d psi 1 star into dou psi 2 by dou n minus psi 2 transpose dou psi 1 star by dou n. Okay, and this is dl, where dl is the line element along the boundary. So you see that on the boundary what is psi 2? What is psi 2? Psi 2 is of the form some Ez2 Hz2, that is psi 2, that is psi 2. And what is psi 1? Psi 1 is of the form some Ez1 Hz1, two different fields, Hz1 different fields. So you know that and the boundary conditions are that Ez1 vanishes on the boundary, Ez2 vanishes on the boundary, and dou Hz2 by dou n vanishes on the boundary, dou Hz1 by dou n that also vanishes along the boundary. So if you see a term of this sort, what is it? It is equal to Ez1 star, Ez1 bar or Ez1 bar or Ez1 bar into dou E Z2 by dou n cap plus Hz1 bar into dou Hz2 by dou n. Because psi is a vector, this will become a row vector consisting of components Ez1 bar, Hz1 bar. This will be a column vector, psi 2 will be a column vector consisting of components Ez2 and Hz2. So if you look at this combination, now Ez1 vanishes on the boundary, so this term will drop off. On the other hand, dou Hz2 by dou n vanishes on the boundary, so this term will also drop off. Likewise for this one, right, this will be, the second term is nothing but Ez2 into dou Ez1 bar by dou n cap plus Hz2 into dou Hz1 by dou n. So dou Hz1 by dou n vanishes on the boundary and Ez2 vanishes, so both these terms will drop off. So this entire term by virtue of the boundary conditions becomes 0, which means that this is a Hermitian operator. This becomes 0, which can also be written as psi 1 comma del perpendicular square psi 2 is equal to this can be written as del perpendicular square psi 1 comma psi 2. But the star, where I make the convention that u comma v is nothing but integral u star v dx dy over the cross section. So this can be written in this. So this equation shows that del perpendicular square is a self-adjoint operator, so it will have real eigenvalues, and it is also negative definite. That is, if you take any psi and you take comma del perpendicular square psi, this quantity is less than or equal to 0. That follows from the fact that if you write psi star del perpendicular square psi plus apply Green's theorem in this form plus del perpendicular psi star psi, which means norm of mod of this square, this quantity dx dy over the cross section of the guide is equal to integral dou by dou n. So this is nothing but psi star into dou psi by dou n dl along the boundary, and along the boundary you have seen that this term will vanish, because this can be written as Ez star Ez bar into dou Ez by dou n cap plus Hz bar into dou Hz by dou n, and dou Hz by dou n vanishes on the boundary and Ez vanishes on the boundary, so this term drops off, this gives you 0, which is same as saying that what is del perpendicular psi star? Del perpendicular psi norm square is del perpendicular psi, it is a 2 cross 1 vector star del perpendicular psi. This is a 2 cross 1 vector, this is a 2 cross 1 vector, star means conjugate transpose. So this quantity becomes 0, which is same as saying that this quantity is equal to, that is, if you look at psi comma del perpendicular square psi, this quantity is nothing but this, and that is equal to minus of integral, let us use a single mod to denote length of the vector. So this is equal to minus of del perpendicular psi square dx dy, right, which is equal to minus of norm of del perpendicular psi square. Norm means you integrate the modulus over the entire cross sectional region, and this is always less than or equal to 0. So this shows that del perpendicular square is a negative Hermitian operator. It is a negative definite, del perpendicular square is a negative definite Hermitian operator. So if you write down the eigenvalue problem in this form, del perpendicular square plus h naught square into psi plus fx into dou by dou x plus fy into dou by dou y. These are 2 cross 2 matrices into psi plus g times psi is 0 after multiplying by a factor of delta, and apply perturbation theory. So, you want to see these terms are coming from the inhomogeneity and anisotropicity. So, h naught square, it will get perturbed by a small amount delta h1 square. H naught square is the modal eigenvalue. It gets perturbed by to delta h1 square on the introduction of the inhomogeneity and anisotropicity, and likewise psi gets perturbed from psi 0 to psi 0 plus delta times psi 1 up to order delta, plus here you will have plus these two terms, that means delta times fx dou by dou x plus fy dou by dou y multiplied plus delta times g, this whole thing multiplied by psi 0 plus delta psi 1 equal to 0. Of course, already there is a delta sitting in these perturbation terms, so it will not contribute. So, delta term delta psi 1 will not contribute to anything. So, up to order delta you can forget about this. So, you equate coefficients of delta power 0 and delta power 1 on both sides. What do you get? You get del perpendicular square plus h naught square acting on psi 0 is 0, and del perpendicular square plus h naught square acting on psi 1 plus delta times h1 square. So, h1 square times psi 0, that is the order delta term, plus fx into dou by dou x plus fy into dou by dou y acting on psi 0 plus g times psi 0 is 0, where fx, fy and g are functions of x, y, omega and h naught square. So, if you solve the unperturbed equation, this is the unperturbed equation, this is the perturbed equation, first order perturbed equation. So, if you solve the unperturbed equation, since this is a Hermitian operator, you will get modal eigenvalues h0n square, right, that is the solution, those are the eigenmodes corresponding to the unperturbed problem in the absence of any inhomogeneous anisotropicity, say n equals 1, 2, so on. So, you solve this boundary value problem, and let us say the degeneracy of h0n is dn, right, that means corresponding to each h0n I have a degeneracy of dn. Of course, it will not depend on p, this equation will not depend on p, whereas this equation will depend upon p, namely the mode along the z direction. That is because fx, fy, fz, they are all functions of omega, h naught square, x and y, and you are going to put omega equal to the unperturbed frequency, namely omega np. The unperturbed frequency is omega 0 np, and in place of h0 square you will put h0n. h0n won't depend on p. So, what is omega 0 np? Omega square epsilon 0 mu 0 plus h naught n square, sorry, plus gamma. Gamma is j pi p by d. So, minus pi p by d square is equal to h0 n square, which is same as saying where omega is omega 0 np, the unperturbed oscillation frequency. So, omega 0 np can be written as 1 upon root mu naught epsilon naught into h0 n square plus pi p by d square power half, where n and p are integers. And if you then write down these equations as del perpendicular square plus h0 n square, and then here you have the perturbed equation is psi 1 plus h1 square. So, you are writing h0 square as h0 n square plus delta times h1 square. You want to see to what mode will h0 n get perturbed when you apply the inhomogeneity in the medium. So, h1 square times psi 0 n, or psi, let us call it as psi 0 to start with. So, plus fx is now a function of omega 0 np, and it is also a function of h0 n square. h0 n square xy into dou by dou x plus etc. Similarly, Fy is a function of the same things into dou by dou y plus G is a function of the same things into nothing. This whole thing acts on psi 0 to give 0. So you have solved for a given value of h0n the possible values of psi 0, the possible eigenfunctions. So you are looking at the eigenspace of del perpendicular square corresponding to the modal eigenvalue h0n square, and you construct an orthonormal basis for this eigenspace. Anyway, for different n's the two will be orthogonal because the eigenfunctions of a Hermitian operator corresponding to two different eigenvalues are orthogonal, and for if you take two eigenfunctions having the same eigenvalue, you can also you look at the eigenspace corresponding to the same eigenvalue of the unperturbed operator. So you can construct an orthonormal basis for such a space and let that let the basis be given by unk. So it will be unk xy k equals 1 2 etc. dn. So this forms a basis, this forms a, if you look at this forms an orthonormal basis. The span of this is an orthonormal basis for the null space of del perpendicular square plus h0n square. Okay, it is a basis for this Hilbert space, and it is a dn dimension, it has got a dimension degeneracy of dn. So you have a set of dn mutually orthogonal eigenfunctions, orthonormal eigenfunctions, that is they are orthogonal and each one of them is normalized to have a norm of unity over the Hilbert space L2 D with two components. So you can say two components L2D plus L2, you can say L2D plus L2D, direct sum L2D. Now you take the inner product of both sides. So what you do is when they switch on the perturbation, then psi 0 cannot take any arbitrary linear combination values of any arbitrary psi 0 cannot be an arbitrary linear combination of the un case, only a specific linear combination will work. This is just as you have the theory of secular determinants in quantum mechanics when we do time independent perturbation theory. So you assume that psi 0 is of the form summation Cnk into Unk of xy of x and y, k equals 1 to dn, like this, and you substitute this into that equation, you get del perpendicular square plus h0n square acting on psi 1 plus h1 square into psi 0. Psi 0 is simply psi 0 is given by this, so this is psi 0 plus other terms f1x and etc. acting on psi 0 is 0. So if I take the inner product on both sides with unk, say I take the inner product with umk, or let us call it as ums. So ums comma del perpendicular square plus h0n square acting on psi 1. What will this give you? Since it is a Hermitian operator and this corresponding to the same boundary, provided you impose the same boundary conditions on all these functions, namely that the first component vanishes on the boundary and the normal derivative of the second component vanishes on the boundary, then this will come to this side, this will be equal to del perpendicular square plus h0n square acting on ums comma psi 1, and ums has got an eigenvalue of minus h0m square. So this will give you simply h0n square minus h0m square multiplied by ums comma psi 1. So ums comma psi 1, you get this, and you will get the, so and the other terms, the second term will give you h1 square plus h1 square into psi 0 has been substituted. You are substituting this expression for psi 0 and you are taking the inner product with ums. So if you use the fact that ums comma unk, this is equal to delta mn delta sk, because for different m's, when m and n are different, these two eigenvectors, these two eigenfunctions are these two eigenfunctions correspond to different modal eigenvalues h0n square and h0m square. So they are orthogonal because they are the eigenvalues of the eigenfunctions of a Hermitian operator or the eigenfunctions of a self adjoint operator corresponding to two different eigenvalues are orthogonal, and for a given value, suppose m equal to n, then it is orthogonal because the two are orthogonal because you have chosen u and k to be an orthogonal basis, an orthonormal basis for the eigenspace of del perpendicular square corresponding to the modal eigenvalue minus h0 n square. So within each eigenspace any two eigenfunctions are orthogonal by our choice. You can always make them orthogonal by choosing a basis of functions and then applying the Gram-Schmidt orthonormalization process. So you will get this h1 square into ums comma psi 0. What will be ums comma psi 0? Comma psi 0, from this you have substituted for psi 0 this expression. So it will be simply C and it will be CMS, it will be simply CMS. Okay, so you will get h1 square into CMS, h1 square into CMS plus the other terms, plus you will have ums comma fx. So it will be f1x or fx dou by dou x plus fy dou by dou y plus g times psi 0, and for psi 0 I have substituted this. So you write it as unk into cnk and summed over all the k's, right. The sum of all these terms is 0. So if you take n not equal to m, you will get a value for ums comma psi 1, provided, and this term will drop out, h1 square times psi 0, h1 square times psi 0 it will not drop out because you still have to calculate h1 square. So you will get an equation for ums comma psi 1, namely you will get an equation for ums comma psi 1 in terms of you will get something like h0 n square minus hms square, sorry, h0 n square minus h0 m square, h0 m square. You will get this is equal to plus h1 square times h1 square times CMS, h1 square times CMS plus those other terms will be summation C and k, k goes from 1 to dn into a matrix that you will get. So that matrix is that ums comma all that, right, that matrix is ums comma fx dou by dou x plus fy dou by dou y etc. acting on u and k, and these matrices depend on omega 0 np as we saw, and they also depend on h0 n square. So these matrices can be written as some functions of, so you can write this as some matrix A which depends on so it depends on omega 0 np, okay, it depends on omega 0 np and also it depends on h0 n square, okay, this secular matrix, and it's also, and you are looking at the for a fixed value of m it will depend on mn, of course it will depend on mn through this inner product, and it will also depend on s and k, okay, depend on s and k. So this is 0. So if you know the value of h1 square, the values of h1 square, you can solve this equation to get this these inner products psi 1 for different, for provided m is not equal to n. So as we do in quantum mechanical perturbation theory, the m equal to n inner product, this inner product corresponding to m equal to n, that is not determinate because that will not appear, that will appear with a 0 factor. If you put m equal to n, this becomes 0. So you have determined this for m not equal to n, and you can reconstruct the perturbation in the eigenfunction or the perturbation in the electric z component of the electric field and magnetic fields as simply ums multiplied by ums comma psi 1 by summed over all m and s and m not equal to n. But now the question, how do you determine h1 square? You do not know the possible values of h1 square, right. So that will come by putting n equal to m in this equation, when this will vanish. So you will get the equation as h1 square. If you put n equal to m, you get CNS, this term becomes CNS, this will drop out on putting n equal to m, this will drop out. So this plus summation So, this will become a matrix, this will be say A of omega 0 np H0 n square, and then here you will have so it will depend, so you will have Sk into Cns, Cnk, okay. K goes from 1 to Dn, this is 0. So, you can write this equation as, if you arrange this in the form of a vector Cns, Cnk, k equals 1 to Dn, you call this as the eigenvector as Cn, then you get an equation of the form A of omega 0 np comma H0 n square, H0 n square multiplied by Cn equals minus H1 square into Cn. So, the possible values of H1 square are the solutions of the equation A of omega 0 np comma H0 n square plus H1 square into identity of size Dn cross Dn, this is 0. So, the values of H1 will depend on both n and p. So, the solutions to this H1 square are what? They are H1 square, and they will depend on n, they will depend on p, and there are Dn of them. So, you write them as k, where k equals 1, 2 etc. Dn. So many possible, each model eigenvalue will get split for each value of p into Dn values. So, you can say that the perturbation lifts the degeneracy of the system, and you can actually get the perturbations in the frequencies. How do you get the perturbations in the frequencies? Simply use the fact that omega square epsilon naught mu naught plus gamma square, which is minus pi p by d square equals H0 n square. So, this was H0 square, which is now equal to H0 n square plus delta times H1 square. It depends on n, p and k, where k goes from 1 to Dn. So, for each value of p, remember that H0 n does not depend on p, on the z mode, on the z component mode. It depends only on the xy mode, it specifies only the xy modes, whereas H1 square will depend on both the xy modes n as well as the z mode p. That is because the secular matrix A1 square which you got, that dependent on the frequency, unperturbed frequency of oscillation, namely omega 0 np. So, if I write omega as omega 0 np plus delta omega 1, delta times omega 1, I get omega 0 np square is of course given by the unperturbed solution to this. So, you write it as delta omega 1 square is equal to H0 n square plus delta times H1 square at npk, okay, plus pi p by d square, So, if you equate coefficients of delta power 0, you get the usual formula, namely omega 0 np square is equal to H0 n square plus pi p by d square. If you equate coefficients of delta on both sides, you get 2 omega 0 np multiplied by omega 1 is equal to H1 square npk, or equivalently omega 1 is equal to H1 square npk divided by 2 omega 0 np. So, you get the possible shifts in the frequencies, and these shifts in the frequencies depend on np, the xy modes and the z modes of the unperturbed system, as well as the degeneracy number, okay, k. So, for a given value of n and p, there are the frequency splits into dn possible frequencies. Okay, it splits into dn possible frequencies on application of the anisotropicity and inhomogeneity in the medium that fills the cavity. I think I will stop at this point. Thank you.